Today we're going to take a look at a concept that is known as a rate of change. In calculus, one of the biggest questions we're interested in investigating is how fast or how slow is something changing. We're really studying the change. The most common example in business is what's called a marginal analysis, where we look at what is the cost of one more item, how much is that going to change our profit, our revenue, our expenses. And so when we're studying change, that's really true calculus. So rates of change, first let's define exactly what a rate of change is talking about. Basically, we're investigating how one variable changes in relation to another variable. So, kind of a picture of what we're looking at here. We have this grid here, and I put some graph on it. Maybe it looks like this. And I'm interested at some point, we'll call it A, which means on the graph, that's the point f of A. And another point B, so on the graph, that's the point f of B. I'm interested in how it changes from one point to a next. In other words, we're really looking at the slope of the line. Tomorrow we'll start calling it a secant line. But the slope of the line from one point to the next. How far we rise and run, that's going to be our average rate of change between points A and point B. Well, we know how to calculate the slope of a line. The slope of a line we'll recognize is y2 minus y1 over x2 minus x1, or how far up we go divided by how far over we go. So in terms of this function, our slope, our average rate of change, is the difference in the y's, or the heights, so f of b minus f of a, y2 minus y1, over the x values, which are b minus a. This formula, f of b minus f of a over b minus a, we call this the formula for the average rate of change. On average, how fast is this function changing between a and b? This is going to be the key function to calculate the average rate of change. So, for example, let's say I did a practice run of a 5K, 3.1 miles, but I timed my run at various intervals, let's say every kilometer. So we've got a certain amount of time and the number of kilometers that were completed. So time's going to be in minutes. Distance is in kilometers. So at 0 minutes, I had traveled 0 kilometers. At 4.2 minutes, I had traveled 1 kilometer. At 8.9 minutes, I had traveled 2 kilometers. At 14 minutes even, I had traveled 3 kilometers. At 18.3 minutes, I had traveled 4 kilometers. And at 23.1 minutes, I had traveled the entire 5 kilometers. And so we're going to be interested in what's my average speed along the way. Let's find my average velocity Velocity is the average rate of change between 1 and 4 minutes. Actually, let's pick some better values. Let's say my average velocity between kilometer 2 and 4. So time, that's my x value. That's an independent variable. It doesn't depend on anything. The amount of kilometers that I travel, that depends on how much time has passed. So y2 minus y1, we're looking at 2 kilometers and 4 kilometers. So y2 minus y1, 4 minus 2, over the 18.3 minus the 8.9. When we subtract, we get 2 over 9.4, which when we divide 2 by 9.4, we'll end up with, I'm running about 0.2128 kilometers per minute on average. Now, depending on how many turns, how many hills, whether I got tired, stopped for a drink, along the way in the middle, I might be traveling a little faster, a little slower. But on average, between kilometers 2 and 4, I was traveling about 2.128 kilometers per minute. And if we change the spread, we're going to get a different average. Let's say we look at the average velocity between kilometers 2 and 3. So now in green here, we're looking at kilometer 2 again, but this time kilometer 3. So my slope, y2 minus y1 is 3 minus 2, over x2 minus x1 is 14 minus 8.9. Well, when we use our calculator to help us out a little bit on the subtraction, 3 minus 2 is 1, and 14 minus 8.9 is 5.1. And 1 divided by 5.1, I see there my average velocity, my average rate of change is 0.1961 kilometers per minute. So it seems I sped up on the next kilometer to pull my average velocity up. So between 2 and 3, average velocity of 0.9161. Between 2 and 4, average velocity increased to 0.2128. We can also use equations to do much the same logic. Let's say we find out that the profit our product makes in hundreds of dollars can be found, or at least estimated, by the equation p of x equals 3x squared minus 2x minus 12, where x is the number of months that have passed. And so we're interested in the average change in profits between maybe months 2 and 5. Well, we need to know what happened at month 2 and month 5. So we're going to do p of 2. That's 3x squared minus 2x. Oops. We're going to plug a 2 in there. 3 times 2 squared minus 2 times 2 minus 12. Our calculators can quickly calculate this by just typing it in like it looks. 3 times 2 squared minus 2 times 2 minus 12 is negative 4. Woo! Negative 4. We're losing money there. P of 5 finding out what's happening in month 5, we do 3 times 5 squared minus 2 times 5 minus 12 equals, bring up the calculator, 3 times 5 squared minus 2 times 5 minus 12. Now we're up to a positive 53. If we want the average change in profit, then we can use that formula that we found up above. Remember, that formula said the slope was equal to P of B minus P of A all over B minus A. So our first point is A and our second point is B. So P of B, that means P of 5, minus P of A, the first point is 2, all over B minus A, all over 5 minus 2. So P of 5 we found out was 53, minus P of 2 we found out was negative 4, all over 5 minus 2, that's going to be 57 over 3. And if we divide 57 by 3, we get our slope, our average change in profit of $1,900,000. I'm sorry, it's in hundreds. $1,900 per month. On average. So between months 2 and 5, on average, our profit went up $1,900 per month. It's a good couple of months. That's this idea of average rate of change. On average, how is it changing between here? Let's do one more using that formula. B. Let's shrink down our window. We were going between months 2 and 5 last time. Let's just go between months 2 and 3. The average change in profit between months 2 and 3. Much the same way, we need to know what's happening at month 2. We need to know what's happening at month 3. And then we'll make 2RA and 3RB and plug it into our formula. So P of 2, we already did P of 2 before. We know P of 2 is equal to negative 4. We don't have to calculate that again. Did that in part A. P of 3, though, that's going to be 3 times x, which is 3 squared, minus 2 times 3, minus 12. So 3 times 3 squared, minus 2 times 3, minus 12, and we got a profit of $900. And so going back to our formula, that of P of B minus P of A, all over B minus A. In this case, that's P of 3 minus P of 2, all over 3 minus 2. P of 3, we found that out as 9, minus P of 2 is negative 4, all over 3 minus 2. So when we do that, we get 13 over 1, saying that on average, between months 2 and 3, our profits changed about $1,300 per month. And because it's positive, we'll even say it was increasing. It increased an average of $1,300 per month between months 2 and 3. Now, this average rate of change bit is something we really could have done in pre-calculus or even in finite math. But we want to take it one step further. Instead of looking at what happens on average over time, how is our profit changing with time, we're going to be interested in how much is our profit changing right now. Right now. So B When we want to know what's happening right now, how are things changing right now, we call that the instantaneous rate of change. So let's look at a picture here, kind of get an idea of what's happening. We'll dive into this picture more tomorrow. But let's say we've got some value here of x. And so then the height, that's going to be f of x. And then we're going to go over some distance h. So we've got x plus h. The height then is going to be f of x plus h. And so again, if we wanted to find the slope of this line, that would tell us the average rate of change. This is what we just did before. It was y2 f of x plus h minus y1 f of x all over y2, which is x plus h, minus let me try that again. x2, which is x plus h, minus x1, which is just x. And you might notice this is nice because we've got plus x minus x. That subtracts out to 0. So we're going to simplify this a little bit to f of x plus h, it's a really bad h, minus f of x all over h, which is really what we just did before. That's the average rate of change between x and x plus h. But we want to know the instantaneous rate of change. We want to know how it's changing right at that point f of x. And so the idea is we shrink the size of h. So if we shrink h down to here, we get this line, which is a little bit closer to how it's changing. And we shrink h a little bit more, we get this line, which is a little bit closer to how it's changing. And we're going to shrink h all the way down until h doesn't exist at all. And we will get this line here, which hopefully will just barely tap my point. And the slope of that line is the rate it's changing at the moment x. And the way we got there is we shrank h and shrank h and shrank h until h was basically nothing. What I mean when h is nothing is I mean we're taking the limit as h shrinks down to 0. The limit as h goes to 0 of f of x plus h minus f of x all over h is going to give us the instantaneous rate of change. The instantaneous rate of change. This is the big formula of the day, and actually a big formula of calculus. The limit as h goes to 0 of f of x plus h minus f of x all over h tells us how things are changing right at this moment. Right now, how is it going to change? So for example, let's say the distance of an object in motion from a starting point is d of t, the distance related to t, equals 2t squared minus 8t plus 7. We are going to attempt to find the instantaneous velocity. Velocity is the rate of change of the distance over time at time equals 1 second. So we're interested at the point t equals 1. So first we do have to find out what d of 1 is. d of 1 is 2 times 1 squared minus 8 times 1 plus 7. And that's going to be equal to 1. So we know d of 1 equals 1. And then we're going to take the limit as h goes to 0 of f of, we're interested in time equals 1 second, so 1 plus h minus f of 1 all over h. Now here's the catch. We can't just stick 0 in for h because 0 is on the denominator of the fraction. And if 0 is in the denominator, the whole thing becomes undefined. So we're going to have to do a little bit more playing. So the first thing we're going to attempt to find is what is f of 1 plus h. F of 1 plus h. That requires us to stick 1 plus h in for both of the variables. So we have 2 times 1 plus h squared minus 8 times 1 plus h plus 7. Order of operations says we have to do the exponents first. So we have 1 plus 2h plus h squared times 2 minus 8 times 1 plus h plus 7. Distributing through, we get 2 plus 4h plus 2h squared. Distributing again, minus 8 minus 8h plus 7. And are there any like terms? Yeah, the 2h squared first. We'll start with that. Then on the h's, we've got 4h minus 8h is negative 4h. And then 2 minus 8 plus 7 is 1. Plus 1. So we now know that f of 1 plus h is 2h squared minus 4h plus 1. We know, we probably should have d's actually, not f's. We know d of 1 is equal to 1. So when we go back to our formula here in the middle, we want the limit as h goes to 0 of the fraction d of 1 plus h, that's 2h squared minus 4h plus 1, minus the d of 1. Well, d of 1 is just 1 all over h. Put a little space here to separate the green. Keeping working. Combining the like terms, 1 minus 1 is 0, so we have the limit as h goes to 0 of 2h squared minus 4h all over h. Remember, to reduce, we have to first factor out the h. So we have the limit as h goes to 0 of h times 2h minus 4 all over h. And now the h's divide out, and we're left with the limit as h goes to 0 of 2h minus 4. Now we can plug in the h equals 0 into the h, because now it is no longer undefined. When we plug 0 in, we have 2 times 0 minus 4. We get the answer of -4. So at this point of 1, at 1 second, the average velocity is -4. In fact, let's write that down. What we just found out is at 1 second, the instantaneous velocity. At that moment, the rate the object is changing in terms of its distance over time is equal to -4. I don't think I put units on there. Let's put in meters. It's -4 meters per second. I want to do 2 more examples, and then we'll come back and talk about what that negative means in terms of the velocity. So let's try another example with the same problem. I'm just going to rewrite it. D of t is equal to 2t squared minus 8t plus 7. And we're going to find the instantaneous velocity at time equals 2 seconds. How are things changing at the moment of 2 seconds? Is it getting closer? Is it getting farther? How fast is it moving? Let's find out. We know to find out the instantaneous velocity, we're going to have to find out what d of 2 is. And we're also going to have to find out what d of 2 plus h is. Those are the 2 parts that we're going to use in our formula. So d of 2, that's 2 times 2 squared minus 8 times 2 plus 7. Calculator. 2 times 2 squared minus 8 times 2 plus 7. -1. D of 2 plus h, we've got 2 times 2 plus h squared minus 8 times 2 plus h plus 7. Simplifying, order of operations says to do the exponent first. So we got 4 plus 4h plus h squared. Everything else the same, minus 8 times 2 plus h plus 7. Distribute through both sets of parentheses. We have 8 plus 8h plus 2h squared minus 16 minus 8h plus 7. Combining like terms, we've got the 2h squared. 8h minus 8h, that's nice, that's 0. 8 minus 16 plus 7 is -1. And so here's the 2 pieces we need. D of 2 equals -1. D of 2 plus h is 2h squared minus 1. So when we go to the formula for instantaneous rate of change, it's the limit as h goes to 0 of d of 2 plus h minus d of 2 all over h. Plugging in what we know, d of 2 plus h, that's 2h squared minus 1. Then we subtract d of 2, subtract a -1, all over h, and we still have the limit out front. Don't lose that limit. That makes a big difference. We're not just simplifying, we're taking the limit as h goes to 0. And when we add that, we have the limit as h goes to 0 Negative 1 minus a negative 1, that's gone. So we have 2h squared over h. And that's great, because we don't have to factor. There's no adding and subtracting. We can just reduce out an h with one of the h's, and we have the limit as h goes to 0 of 2h. It's not undefined anymore. There's no denominator, so we have 2 times 0, which is equal to 0. What we just found out was that the instantaneous velocity at time equal to 2 seconds is 0 meters per second. The change in position is 0 meters per second. Let's do one more example, and then we're going to come back and talk about what all three of these mean as we look at this instantaneous velocity. What's happening at that moment? So one more example. I'm going to write the function down again just so that I can see it, and it was a d of t. I keep wanting to make it f. The distance with respect to time is equal to 2t squared minus 8t plus 7. And we're going to find the instantaneous velocity at time equals, well, we just did 2. Let's do time equals 4 seconds this time. So we're going to need to know what d of 4 is, and also what d of 4 plus h is. Okay. Well, d of 4, plugging 4 into the formula, we have 2 times 4 squared minus 8 times 4 plus 7. Calculator, 2 times 4 squared minus 8 times 4 plus 7 is 7. d of 4 plus h, that's 2 times t, which is now 4 plus h squared, minus 8 times t, which is 4 plus h, plus 7. Simplifying, we do the exponent first. 4 squared is 16, plus twice the product, 8h, plus h squared, minus 8 times 4 plus h, plus 7. Distribute the 2 through, we have 32 plus 16h plus 2h squared minus 32 minus 8h plus 7. Combine like terms, there's the 2h squared, 16h minus 8h is plus 8h. 32 minus 32 plus 7 is plus 7. Now that we know those two parts, we can go to the formula for the instantaneous rate of change. The limit as h goes to 0 of d of 4 plus h minus d of 4 all over h. d of 4 plus h, we just found that. That's 2h squared plus 8h plus 7. Minus d of 4, we just found that. That's equal to 7. Oops, but I forgot the limit part, so I'm going to start over, because do not forget to write the limit as h goes to 0. Notation is important because it's going to change the meaning. 2h squared plus 8h plus 7 minus d of 4 is 7 all over h. Combining like terms in the numerator, that's really nice because we've got a 7 minus 7, which is 0. So we have the limit as h goes to 0 of 2h squared plus 8h all over h. Before we can reduce the fraction, we first have to factor out an h. So we now have the limit as h goes to 0 of h times 2h plus 8 all over h. And now that it's a factor, now we can reduce out the 4, giving us the limit as h goes to 0 of 2h plus 8. And now that the denominator is gone, the fraction will no longer be undefined. We plug 0 in. We have 2 times 0 plus 8, which we can see is 8. What we see is the instantaneous velocity, or the rate of change, at time equals 4 seconds is 8 meters per second. Instantaneous velocity. Let's look at these three answers and kind of talk about what they mean. If the instantaneous velocity in this example at 4 seconds is 8 meters per second, that's the rate it's changing. The distance changes 8 meters per second. Really, that means at this moment, he is getting 8 meters per second farther away from the starting point. That's his rate of change. And because it's positive, he's going to be 8 meters farther away each second at this moment in time. Now his velocity is going to change, but at this moment, right now, 8 meters per second is his instantaneous velocity. Compare that to what we got in part B, where we said the instantaneous velocity at 2 seconds was 0. Which means at 2 seconds, at that moment, it's not getting any farther or closer. It is stationary. At 2 seconds, it is going to stay where it's at until it changes its direction. And then if we go up a little further to the first example, at exactly 1 second, the instantaneous velocity was -4 meters per second. -4 means it was going backwards. It was coming closer to the original point. It wasn't going away, it was coming closer. So at 1 second, it was getting closer until at 0 it stopped, turned around, and went back. So it was coming closer at 4 meters per second. Then by 2 seconds, it had stopped. And then by 4 seconds, it was running away at 8 meters per second. Instantaneous velocity tells us how it's changing at each moment instantaneously. So a quick review. There were two formulas we set up today. The first one was f of b minus f of a all over b minus a. Told us the average rate of change. If I can write average. There we go. The other big formula was the limit as h goes to 0. Instead of using b and a, we used x and moving over h, so we had f of x plus h minus f of x all over, and when we subtracted the b minus a, it simplified to just h. That is the instantaneous rate of change. Those are the two big formulas for today. The big one being the second one. We're going to play with that a lot over the next couple days. But until then, take a look at the homework assignment. Try some of these rate of change problems, especially focusing on the instantaneous rate of change. And we will see you tomorrow in class with questions.